Okay, this is AP Calculus, section 6.2, page 3. We are still working on some U substitution. Let's start right here on number 9. And we see that we have both a quantity inside of a cosine function and a sine function, and we also have something raised to a power. So we have a couple of options here to use for U. We could choose u as 3x minus 5, or we could choose u equals the sine of 3x minus 5. Actually, in this case, both of them will work. It's a little bit easier, though, if we look at u is the sine of 3x minus 5. Then du would be cosine 3x minus 5 times 3 dx. Substituting in just for the u, we are going to have cosine of 3x minus 5 over u squared dx. And then this piece right here, cosine 3x dx, is what we need to replace out. And we see right here, cosine 3x minus 5 dx is going to be 1/3 du. We can pull that 1/3 out. We have this u squared down here and a du up there. Be careful, this is not a natural log situation because we have a power here, this u squared. If this was just a linear term, then we're talking natural logs when you do an antiderivative. But this power takes us away from the natural logs. Let's rewrite this as u to the negative 2 du. Now we can anti-differentiate. Add 1 to the exponent gives us u to the negative first. Divide the coefficient by the new exponent. Puts a negative 1 out here. Plus a c. And we're looking at negative 1/3 u to the negative first. Plus a 1/3 c, which is just a different c. Now, I would suggest you rewrite this u to the negative 1 as negative 1 over 3u plus a c. And now we see negative 1 over 3 sine of 3x minus 5 plus a c, which can then be further written as negative 1/3 cosecant of 3x minus 5 plus a c for our final answer here. Looking at this next one, we're running into some trouble here because we don't have anything on the inside of a trig function that's different than just x, and we have no powers. So we have to remember our pre-calculus and go back to, oops, I got to lower this down so you can see it. I'm so sorry. We have to go back to pre-calculus, and we know that tangent is sine over cosine. And we have a couple of options. We have the two functions here, a sine and a cosine, and we could choose u is sine x, or we could choose u to be cosine x. Let's try this one. U is sine x, then du is cosine x dx. And when we replace that out, the u is up here, cosine x in the denominator, times the dx. And we are trying to replace out that cosine x dx. We have trouble here because, notice, this cosine is in the denominator. So we have dx over cosine x. This one is cosine x times dx. That's a problem. This was the wrong choice. So let's try this one, and hopefully this one works. If u is cosine x, then du is negative sine x dx. And when we start to substitute out, we have the u in the denominator, and we'll have a sine x dx left up there in the numerator. And now look, we are trying to replace out this sine x dx, which is right there. So that sine x dx can be replaced with negative du. I'm going to go ahead and pull that negative out. So we have du over u. We are also now in completely u's, so we can change the bounds. This upper bound will be the cosine of pi over 4, or square root 2 over 2. Down here is cosine 0, which is 1. Some of you will see this antiderivative as written. Others of you will like to rewrite it as 1 over u du. Now we have that natural log situation going on here. And we'll have negative natural log, absolute value of u, evaluated from 1 to square root 2 over 2. And that'll give us negative the natural log of the absolute value, square root 2 over 2, minus negative natural log absolute value of 1. ln 1, you just have to know that by now, that the natural log of 1 is 0. So we have negative natural log absolute value of square root 2 over 2. Well, square root 2 over 2 is positive, so we don't need the absolute value bars. And we look at this and we think we're done. Except on a multiple choice test, if you start looking for your answer is not there. So we need to go through and manipulate this and see if we can get it to match another answer. I'll tell you what the answer is. Is the natural log of the square root of 2. So we need to remember some pre-calculus here. Did your teacher ever use the word leaping exponent? I always called it a leaping exponent because that coefficient out here can leap up and become an exponent. Or sometimes it can leap down and become a coefficient. So we are now looking at this as being the natural log of square root 2 over 2 to the negative first, which is the natural log of 2 divided by the square root of 2 because of that negative 1 exponent. Rationalizing out a denominator, and we do end up with the natural log of 2. Okay, again, this procedure of manipulating through some pre-calculus is important for a multiple choice test. On a free response, that answer, negative natural log square root 2 over 2, is perfectly acceptable. Where it's going to be important is if you do this and you're sure you did the calculus properly, but you don't see an answer choice, you have to be able to manipulate through to get this answer. All right, now coming back over here, there are some other miscellaneous integration formulas. These are not in our current textbook, but it is nice to have them in your repertoire, in your bag of tricks, if you will, when you integrate. The integral, or the antiderivative of a to the u du is a to the u over ln a plus a c. Antiderivative of sine u, you know that one, that's negative cosine u plus c. And you know this one, that's sine u plus a c. Now the antiderivative of tangent u. We just did a tangent one up here. You can always change tangent into sine over cosine and then do the u substitution. Or you can memorize that the antiderivative of a tangent u is the natural log of the absolute value of secant u plus a c. Antiderivative of secant u is the natural log of the absolute value of secant u plus tangent u. The antiderivative of a cosecant is natural log, absolute value, cosecant u minus cotangent u. And the last one, the antiderivative of cotangent u, is the natural log of the absolute value of sine u plus c. Please memorize these. Thank you for joining me on page 3. On page 4, we will do some integrals that apply these new integration formulas.